It was the best of times. It was the worst of times. It was the age of waiting for CI, which takes an age and is my least favorite things to do. Partly because I'm impatient and I'm bad at multitasking, but mainly because if you think about how much time you spend waiting on CI every day, and you multiply that by the number of people in your team, that's a lot of time that we could be using better. Enough that it makes sense to put in some real work to make it run faster. And today, I'd like to tell you about a few techniques that I've used in the past that have given me great results. First of all though, hi, my name is Daniel and I learned all of this working for GoCarless, a payments company based in London. Now, as you probably noticed, I'm not originally from London, I come from Argentina, so in case you were wondering, that's the accent. So, I want to help you make your CI finish faster, and as the title of the talk says, I'm proposing that you do this by throwing lots of computers at the problem. So, I'm not going to talk about how to make individual tests run faster. There are lots of resources out there, using fixtures instead of factories, mocking stuff, lots of techniques shared by people that can explain them way better than me. The problem with these techniques is that they normally involve rewriting your tests, and they normally take an amount of time that is linear with the number of tests that you have. And your test suite is probably huge, or you wouldn't be looking at my face right now, so that's not very fun to do. What I want to talk about is how to reduce the total runtime of your CI test suite with a focus on getting the most impact for the time that you invest. And we do that not by making your tests faster, but by running them on lots of computers at the same time. What I want to focus on is making some systemic changes that are going to let your tests still run slowly and are going to let your team still write tests the way that they used to, but when you're running in CI, you run massively in parallel so you can still finish quickly. Now, of course, what I'm advocating for here is throwing money at the problem in exchange for saving developers' time. And this is not always the appropriate way. But for a lot of companies out there, when you have an engineer with a typical engineer salary, waiting on CI and getting distracted by Hacker News, there are lots of situations where it makes sense to spend as much money as your CI provider will take from you. And to be honest, it's not even that much. I mean, we're using tons of machines and spending on the order of less than $100 per developer per month in total. Now, before I start, I want to make a couple of notes. First of all, you're going to see a bunch of Circle CI on this talk, mostly on all of my screenshots, and I'll also mention a tool or two that they provide. This is because we happen to use Circle at GoCarless. This is not an endorsement in any way. I just happen to have the most experience with them because of my day-to-day work, and it was the easiest way to get screenshots of complex CI setups. And to be fair, I also have my share of frustrations with them. I'm not trying to recommend them particularly, I just happen to have used them a lot. But more importantly, this is not a Circle-specific talk. Everything that I'm going to talk about is around optimizing things that every CI provider will have to do, so it should be applicable to pretty much all platforms. The same thing goes for every time I say RSpec. I'm using RSpec as an exemplar of habit, but almost everything I'll be talking about today will still work with Minitest or any other test framework in Ruby or in other languages. I've actually used a lot of the same advice for a PHP project that we have. And the specifics of the projects could not have been more different, but the thinking behind what I'm going to share applies to pretty much all languages, and that's what's going to help you speed things up. Another thing to keep in mind is that I'm going to show you a bunch of code to explain these techniques. This code is going to be oversimplified, so I can explain the concepts quickly, and some of it is going to move pretty fast. But the talk comes with a supplementary GitHub repo, which you can find here, and there you're going to find fuller code examples, more documentation on how they work, and you can grab them from there as a starting point for your project. Now, unfortunately, most of them you won't be able to just grab and use. You'll probably have to adapt them to your needs, but I've tried to document where you need to adapt them. More importantly, this is not a do these 3 things and you will get this exact result roadmap kind of talk. Your mileage will vary. Your CI setup will be different from mine. The specific things that are slow for you are different from everyone else's. I'm going to share a bunch of techniques, some of which will be super relevant to you, some maybe not as much. This talk is mostly a way to think about the problem of CI times and a bunch of tools and techniques to help you improve those times. But you will need to test these, see which ones help, which don't, and tailor them to your specific situations. Now, I mentioned the PHP project that we had in addition to our Ruby ones, and we've drastically improved runtimes of both of them using these ideas, but some things that made a massive difference to one didn't move the needle at all on the other one, and vice versa. You'll have to adapt these to your needs. So it'll take some work, but it'll be worth it when you no longer need to wait on CI for ages. So measure, experiment, see what works for you. All right, with that out of the way, let's get to it. We want to make our CI suite finish faster, and we're going to do that by running things in parallel. But first things first, how do we even do this? How do we parallelize our tests? And there are two main ways. You can manually split off sections of your test suite into chunks that make logical sense, and then have each of those chunks run in parallel. And then you can take each chunk and automatically split it into many machines to also run it in parallel. Now, this is not an either-or choice. You'll most likely want to do both. So let's start with the simplest one, and it's very likely that you're already doing this, but it's still worth talking about. If you can separate your test suite into different pieces that make sense, which is going to likely be different subdirectories within your specs directory, you can create different CI jobs and call rspect on each of those different directories for those tests. Now, Rails does this beautifully, for example. If you look at their test suite, you'll see that they have separate jobs for active model, active record, action cable, etc. Each of these is a coherent logical unit. It's easy to understand when you're looking at the CI setup, and they all run in parallel. So if your app is super modular like this is a great win. It's a very easy starting point. Now, in most Rails apps, you're going to have integration, models, controllers. This is not as granular, and typically one of those is going to take a lot longer to run than the others, but it's still probably worth separating, and it's a good starting point. Now, two things that you should keep in mind. One advantage of separating these is that you get more granular control over the running of each job. For example, some CI providers will let you choose between different instance sizes, which obviously cost different amounts of money per minute. Now, sometimes, for certain kinds of tests, particularly integration ones, you may need a bigger instance so you can fit all of your dependencies in RAM. Now, if you take those tests and separate them out into their own job, you can pay for larger machines only for the parts of the test suite that need them, and you don't need to make the rest of the tests more expensive. This is our setup, for example, and you can see we have separated search tests. This would normally live under integration, but they had more dependencies than the other, and they needed bigger machines, so we split them out. The other thing you can do is control dependencies between jobs better. For example, your JavaScript tests will need to wait until your node modules get installed, but your model and unit tests probably don't. So if you separate your JS test from your unit test, you don't need to wait for Yarn to finish before your unit tests can start, and then they can start sooner. The same goes for our search example. Most of our tests don't need Elasticsearch to be running, so they don't need to wait for that to boot up. Now, the second thing you want to do is a bit less obvious. You want to have a catch-all job. If you go very granular on the splitting approach, it's very easy to later add a new test subdirectory and forget to add the new CI job for it. If you do this, and you later add a new directory, spec/new tests, you'll likely forget to add a new CI job for it. Your new test won't run in CI, and you will never notice, which is pretty sad and is dangerous. What you want to do instead is have a final catch-all job, and instead of targeting a specific subdirectory to run, you want to find all of your tests and filter out the ones that are already run by other jobs. And using find and grep-v lets you do this very easily. Now, I'm not going to lie, this code is kind of ugly, I get it, but it fails safe. I mean, the caveat is obviously that you need to remember to add an exception here if you later add a new job for some other subdirectory. But now the penalty for forgetting something is that you run some tests twice, which is way better than skipping an entire chunk of them. So I think that safety justifies the yuckiness. So that's how you split your test suite manually, which again, I bet many of you are already doing, but I think it's worth keeping these caveats in mind. The other way of parallelizing, and the one we're going to focus the most on today, is having multiple machines run a single set of tests by automatically splitting the files between them. Now, the key part of how you do this is, instead of giving your test runner a directory to run, you give it a list of all of the files in that directory. And you do this because once you have a list of many files, you can split it into chunks with a little magic. So you do that in many machines. Each machine picks a different chunk of that list and runs only those. And in aggregate, you will have run all of your tests, but each of those chunks basically run in parallel. Now, in order to split this so that no two machines run the same file and that all files get run, all right, wait. Some of you already know how to do this, or you're doing this already, and I can see you reaching for your phone right now to check Twitter. Stay with me for a quick second because I got news. As I said at the beginning, your mileage will vary, and not every section of this talk will be relevant to everyone. So I'm taking advantage of this new interactive Railsconf format to do some unorthodox things that I couldn't do in a live talk. Now the good news is you can skip over things that you already know. If a section might not apply to some of you, I'll make a comment about it, and an icon like that is going to show up in the corner with a timestamp. So if a particular section doesn't apply to you, just skip until the icon is gone and you won't miss a beat. So as I was saying earlier, in order to split this list of files that you need to run so that no two machines run the same file and that all the files get run, each machine needs to know two things: which machine it is and how many total machines there are. And then we can have each machine basically know these two things through two environment variables. And knowing this, each machine can basically take every nth file with an offset at the beginning, and that basically does it. Now, of all the things I'm going to talk about today, this is the one where different CI providers will vary the most. Circle CI, for example, have this CLI tool that is going to help you find your test files, and it will split them for you. Now you specify a parallelism value for how many boxes you want to run, you run a command kind of like that, and it pretty much just works. And if you put in a little bit more work, it can also do smarter allocation based on historical times on each file, which is actually pretty cool. Now, CodeShip has a less ideal approach. It lets you specify a number of steps to run in parallel, and you can embed environment variables right there. And this needs a little bit more work from you. I'll show you in a minute how to use this, but that'll do it. Buddy, for example, has something similar to Circle, where they will split the files for you ahead of time and put the list of files for each machine in these env variables called buddy split 1, buddy split 2, etc. And you can just use those directly, pass them on to RSpec. Now, sadly, most providers don't have any tools to do this directly, but you can do it yourself if you slightly abuse a feature that almost all of them have: the build matrix. Now, most providers will give you a way to run the same job over and over with slightly different parameters, and they call this a build matrix. And the idea is you can run the same test suite over and over with, for example, different versions of Ruby or different gem files pointing to different versions of Rails, and then you can make sure that your code is compatible with all of them. Now, this code above is from GitHub Actions, but they're all very similar. And some of those keywords that you can see up there, they mean something for different specific providers, keywords like OS and RVM or Ruby. But you can make up your own keywords and then use those to set environment variables, like you can see up there. And that means that we can abuse this feature and bend it to our purpose. We can make up a box index in the matrix, and we use that to number all of our boxes. And then we set these two environment variables, the ones I was talking about earlier. And if we do this, we now get 4 boxes. Each box knows which one it is and knows how many there are. And so with a little command line hackery, you can get each box to pick up their part of the split, as I was showing you earlier. Now, this script here is a simplified example, but what we're doing is we're taking all of the respective files and passing them to awk line by line. And in awk, this variable nr will tell you what row of the input you're in right now. So you modulo that by the total count of machines, you compare it to your machine number, and decide whether you want to proceed with this file or discard it. And that gives you the split that you need. That's it. Ta-da! Now, pay attention to that sort there. That's important to keep things consistent, or you may end up with different orderings in different machines. Now again, that code is very simplified. In reality, it looks a bit more like this. But doing this, you can split your test between as many machines as you want and parallelize like crazy. Now again, I admit it, this does look a bit ugly. But if your CI platform doesn't help you split your tests, this works. And if you give it enough boxes, it'll speed up your test massively. Okay, so pretty much all of this so far has been an introduction. I need to explain how we run things in parallel so we can get into the actual main part of this talk. Because now is when things get hard and interesting. Because in theory, there's no limit to how many boxes you could have, right? You can give it 1,000 boxes and your test should run almost instantly. But obviously that's not how that works. The truth is, if you do just this, you can improve your CI times a lot, but it's not going to be ideal. There's a wall that you're going to hit pretty quickly, which is going to be imposed by your startup times. You see, when you run one of these boxes, your tests don't just start running instantly. For most CI providers, these boxes are a container that has to be downloaded, it has to be started, then you need to run a bunch of setup tasks, and only then you're going to run your tests. If you're not careful, you can easily spend 5 minutes doing this setup, and then you start getting very sharp diminishing returns for each extra box. I mean, if you think about it, even if you have infinite machines, if you're doing 5 minutes of setup, it will still take at least 5 minutes to run your tests, right? And also, while I'm all for throwing money at the problem, if you're waiting 5 minutes for each of those boxes, you're going to want a lot of boxes, and that's a pretty big money bonfire for you. So you want to focus on these setup times and make them as small as you possibly can. Now, a typical CI config looks a bit like this. And that last step I highlighted over there, that's where we actually run our tests. But there's a lot of stuff that needs to happen beforehand. Now, at the beginning of the talk, I said I wouldn't talk about how you make your individual tests run faster. All of that work would focus exclusively on that last step I highlighted. And that is what we normally look at to try and make faster. And this makes sense because it's what takes the longest and it feels like we can control it. But here's the thing. Here's how I see this list of steps. That last bit is what's actually doing the work that we want, and is the part that we can parallelize. So if it's taking longer, we can just throw more computers at it. All the stuff that comes before it, that's a necessary evil, but it's waste. And if you have more computers, all of them need to do those steps anyway, so it doesn't parallelize at all. Now the problem with those is that they don't look like you can do anything about it. Your tests, that's your code. You can change it, you can optimize it, you can do whatever you want with it. But a container is going to take as long to start as it takes to start, right? And bundle is just going to take however long it takes to install these gems, and you do need those gems. And all of those steps are necessary. You can't get rid of any of them. So it really doesn't look like you can do much about it. But in reality, we can get clever here, and there's a lot that we can do to start chipping away at those startup times and to make this a whole lot better. So here's what you want to do. Your CI will probably show you something like this with all of the little steps. And again, that's what they look like to me. So what you want to do is look at all the steps that run in your CI job before and after your actual tests and look at the running times. And you want to focus on the ones that are taking a long time and try to start chipping away at them. Now these times are not intended as a weird flex. I just don't have a before screenshot, but believe me, they were a lot worse before we optimized them. And the important point here is you only care about the slow ones. If one of the things that I'm going to talk about next only takes 5 seconds for you, you don't care, you just move right along. If your git checkout is 2 seconds, there's not much point doing trickery to optimize it, right? If it's taking 30 seconds, then it may be worth it. Now, at this point, you might want to pause this talk and take a look at your actual CI setup steps and the runtimes, and that should put the rest of this talk into context and highlight what you want to pay more attention to. And with that in mind, I'm going to talk about 3 things: installing your gems, checking out your code, and container spin-up time. Now, depending on what CI provider you use, some of these bits may involve swimming against the current a bit. CI providers try to make it easy to get started with them, and they do this by giving you a sane default that is very easy to set up and that does reasonable things. And this is great for getting started quickly, but it's not so great if you're trying to squeeze out every last drop of performance from it, because for that, you will want to customize things. And to what extent you can customize things will depend a little bit on your particular CI platform, but from what I've seen, most of them allow doing most of these things, so they just sometimes are going to involve going a little bit outside the beaten path. So, let's talk about bundle first. In order to run your tests, you're going to need your gems installed. And you either let your CI provider do this magically for you, or you install your gems doing something like this. But as you know, installing all of your gems from scratch takes forever. So in order to prevent that, most CI providers give you caching capabilities. Some of them do it automatically for you, some let you do it yourself. But basically what happens is this. Before you install your gems, you control whether they get stored with set path. And then after you install your gems, you save that directory to your CI's cache. Now on the next run, before installing, you restore that cache, which means bundle install is going to run instantly because all of your gems are already there, unless your gem file changed. And you are probably already doing this caching. And when you first set this up, this works great. The first run takes a long time because it needs to install everything, but then your gems are cached, and future runs actually go through this pretty quickly. And every time you change the gem file, you only need to install a gem or 2 that are new, that gets cached, and things continue to be fast. However, over time, you might find that restoring that cache starts taking a longer and longer time. In our case, I've seen a restore time of about 2 minutes at its worst, which is pretty bad. And this happens because as you upgrade gem versions, the old versions are left behind in the cache and they bloat the size of the file that you're saving and restoring and moving around. And to prevent this, you want to tell Bundler to automatically clean outdated versions. When you do this, Bundle will delete all versions of gems that your gem file no longer uses, and that's going to make the CI cache smaller and faster to move around. Now, unfortunately, the specifics of how you do this depend on your version of Bundler. In older versions, for example, you pass --clean to bundle install. So you want to look at the documentation for your specific version of Bundler. And while you're in there, look for other flags that look like they can save you space and experiment with them. Bundler has a lot of configurability. I'm also going to talk about manually deleting uses files a bit later, and that can save you even more space, but it's a bit harder to do. And finally, you want to look at the docs for your CI provider in detail. All of the different CI providers have slightly different features around this that you may be able to use and gain even more time. So keep an eye on those bundling and cache restoring time, and if they get long, this may help. Now, our next step is git checkout or git clone. This is one where you should only spend time on it if you see this step take a while. For a lot of projects, this is going to be pretty quick. But as you accumulate history and your repo gets big, you're going to start taking longer. And if you're taking 20, 30 seconds, it may be worth trying to do a shallow checkout where you only get the last few commits instead of the entire history. Now, this may or may not be faster depending on the number of things, but it is worth trying as a first approach if your checkout is taking a long time. Now, unfortunately, I can't really tell you how to do this in your situation. This is another one where CI platforms will give you very different options, either directly or using some library that somebody has made and you can import. So you want to check the docs for how to do this. I mostly just wanted to call out that this is one to keep an eye on and that a shallow checkout might help. And if that doesn't help, again, I'm going to be talking about how to do this in a different way a bit later with a different approach. All right, so we've talked about two of the biggest usual time wasters. Now let's look at probably the worst one, container initialization time. Now this section is probably the bizarrest one in my talk. I know it will sound like really weird advice, but it can pay off massively if you're having this problem. So give this a shot. Generally, all CI providers will run your stuff on Docker containers. And if you've ever used Docker, you're probably familiar with this site. Now, unfortunately, for this part of the talk to make sense, I need to give you a brief introduction to how Docker works. Docker containers are a sort of separate space in your machine with their own little file system and processes that can't touch each other, sort of like lightweight virtual machines. And just like a virtual machine, they get booted up from an image, which is basically a giant collection of files. And these images, they get created from a set of instructions that you put in a Docker file, which looks a little bit like this. You may say, start from a plain Linux image, install Ruby on it, copy my gem file in it and run bundle install, then copy all the files from my app and take the result of all of that, and that's my image. And you can specify when that image runs, run this command to start my app. That's that last unicorn command on there. And just like you can create your own image, there are lots of common tools like Postgres or Redis which have pre-made images that you can just use. These live in a central registry similar to Ruby gems, and that means you can tell Docker, hey, run me a Postgres and a Redis and this custom image that I made, which is my app. And what Docker does is when you try to run an image, if you don't have it, it'll go to registry and download it for you, just like Bundler does when you install a gem. And when you're running in CI, it's very common to do this. You tell your CI provider, run me a Postgres and a Redis, and also run my tests in a container image that has Ruby 2.7 in it. And most CI providers give you a bunch of handy images that they have pre-made for you. So you may get an image that already has Ruby in it, but also has Node and Chrome in there, so you can easily run your integration tests without having to install everything yourself. And understanding images is good. But if we want to be able to get those containers to start faster, we need to go one level deeper. We need to talk about layers. Because one of the really interesting ideas in Docker is that when building this image of yours, there are things that take a lot of time to run, but they don't change very often. And there are things that do change very often, but they don't take as long to do. So what Docker does is, when it's building your image, at each step in the Docker file, it'll do what you ask, but all of the writing that it does to the file system in that image, it gets stored separately from what's already there from the previous steps. It gets put in a layer. And this layer depends on the previous existing layer and adds or modifies files. And Docker will also take a hash of what you're doing, so that the next time you try to build the same image, if the step hasn't changed, Docker knows that because the hash matches, and it goes, I just use that layer I've got cached over there, and saves you a lot of time. Now in this sample Docker file, you'll be building this part here over and over. But this whole chunk at the beginning doesn't change. You're always installing the same versions of the same thing, so Docker just uses the layer it already has. Now this part does change, because your app files probably changed, and so for this it does need to make new layers, but for everything else it can save itself a lot of time. So the result of this is that your image is not a single monolithic file, it's a stack of layers, and each of them depends on the previous ones, but they can be downloaded and cached independently, and they can also get shared. So that image you started from, it could be anything. It can be your own image if you want, and it can already come with a lot of layers in it. So if you have a bunch of different applications on Ruby 2.7, for example, you may end up making your own base image that includes the installation of Ruby and all the stuff that you have that's common to all of your apps, and then you can reuse that in the Docker file for each app. Now, if you do that, the layers in that custom Ruby image that you made will get shared for all of the apps on the machine. They will only be built and downloaded once. And that shared part is also probably the biggest part of your Docker image, whereas the bottom bit is going to be different for each app and for each build of your app, and so it will have to get downloaded every time, but at least the big ones at the top get reused. And that is what you're seeing when you see this download screen. This is trying to run an image, and it's downloading all of the layers that it doesn't already have. And you've also probably seen something like this, where some layers already exist and those don't get downloaded, and here, for example, we're only downloading one layer. The other ones are already cached. Now, the reason I'm talking about all of this is that depending on whether you get this or this, it's going to make a huge difference to how long it takes to start your containers. You really, really want the machine that runs your tests to already have downloaded the images that you're going to use, or at least a lot of its layers, because if it has, your containers will start almost immediately. And if it hasn't, then you will first have to download probably at worst about a gigabyte, and that can take a while, and then it needs to extract those layers, and only then it can start to spin them up. So you really, really want the machine that's running your tests to already have the layers that you're about to use. Now, unfortunately, you generally have absolutely no control over this. Your CI provider has a gigantic pile of computers, each one of them is running tons of containers for lots of people, and you have absolutely no control over which machine your test lands on, or what layers that will have already cached. And this is why I said earlier that this is a somewhat bizarre piece of advice. I'm basically saying, try to make sure the machine you have no control over already has your layers. That sounds kind of nuts. But what runs in these machines isn't random. You can't guarantee what a machine has already downloaded, but you can try to influence the odds in your favor. There are loads of people that are running their stuff in these machines. Loads of these people are going to be using Ruby. So they'll be using a Ruby image, probably the Ruby image provided by the CI platform. So if you're running Ruby tests, it's quite possible that your machine will have a Ruby image cached because somebody probably ran Ruby tests there earlier. And here's the bit you can control. Not all of the images that you could use will be equally likely to be used by others. Some versions are going to be more common than others. So you're going to have, for example, a lot more people using Ruby 2.7.2 than 2.7.0, for example, just because it's a newer version. And both of them are going to be a lot more common than, 2.3.5, just because it's old. The same goes for Postgres. If you're using Postgres latest, it is way more likely that somebody else has used that recently than if you're using a random outdated version like, 9.6.17. And this really bit us at one point. We were using a weird version for an image that was actually pretty large to download, and our containers were taking ages to start. And just switching to a very similar but more popular version saved us about a minute of setup. So what you want to do is make sure you're using what looks like the most popular versions of your dependencies, so you can load the dice in your favor and increase the chances that the images that you use, or at least a good chunk of their layers, are going to be cached. Now again, this is still weird advice because you have no way of knowing what other people are using. But if you see that your container startup times are high, you can look inside that container spin-up step in your CI platform, and you can look at whether it is frequently downloading layers or if it's using the cache. And if it's downloading things very often, you can start looking at what are the other available images that you could use and trying different ones to see if they get cached more often. You also want to point to less specific versions, which is going to be more common that other people point at them. Now in Docker, you can have many different tags pointing to the same actual image, and these tags can get repointed over time. So for Ruby, for example, you will have tags for 271 and 272, but there's also just 2.7. And 2.7 points to the latest patch version, and probably most people will be using that one as it keeps repointing itself over time. When 273 comes out, 2.7 is going to point to that one instead. And the same happens if you have a latest tag, like Postgres latest or Redis latest. That will generally be the default that most people use, so it's going to be more likely to be cached. Now this advice, it comes with a big disclaimer. All of the things I'm proposing that you do today, like everything in life, they have trade-offs. But this one in particular has a massive one, because one of the glorious things about Docker is that you can specify the exact version of everything and fully control your environment. So the usual best practice is choose the exact version of everything in CI that you're running in production, because then you're testing on the exact same environment or as close as you can get it. Whereas I'm standing here suggesting that you do the exact opposite, and that implies some risk. If you use the latest Postgres, now you're testing on a different version than the one you're actually running in production, and that could bite you. On the flip side, you can save hundreds of hours of developers' times collectively if you do that. So which one matters the most will depend on your particular situation. And there's also some nuance here, some middle ground. For example, you almost definitely don't want Ruby latest, because Ruby changes a lot between minor versions. You may get hit by deprecations, backwards incompatible changes, other problems like that. But if you're using Ruby 2.7.2 in production, pointing to the latest 2.7 is actually probably safe enough, and your CI will probably still be trustworthy. And if you do that, you can get the startup speed benefits of having a more common, more cached version. Now, if you're running an old version of Elasticsearch or some software that has had major backwards incompatibilities, then yeah, you'll probably have to still run that specific version, and that sucks. But for things like Postgres, which have really good backwards compatibility, for example, using the latest one is probably fine. Oh, and make sure you're using the Docker images that your CI provider gives you, not the normal official ones, because that's the ones that everybody else is going to be using and they're going to be more cached. Again, it's weird advice. You're making CI less deterministic, which is normally the opposite of what you want, but speed, so you're going to have to wait this one. The other big disclaimer, of course, is that this is also much less deterministic in terms of timings than anything I've talked about so far. You're always literally rolling the dice on whether your machine is going to have your layers or not. Now, doing this lets you weigh those dice a little bit to your advantage, but it's still a crapshoot. And because of that, it can be harder to gauge whether this helped or not, because the runs that you're serving when you're trying it may or may not be representative. And I'm going to talk a bit more about that later. But the general gist for this is try to use common versions of things if you can, because it can make your containers boot up a lot faster on average. Okay, so we've covered how to speed up bundler, git checkout, and container speedup. But now that I've talked about Docker, I mean, you gotta have that for if you're gonna talk about Docker. Now that we've talked about Docker, I'd like to take a second look at these same three topics, but for a more advanced scenario. If you have the ability to build your own containers and push them to a registry, and if your CI platform lets you run your own containers, there's more we can do to gain even more speed. Now this takes some more work than the previous tips, so maybe it only starts being economical when you start having larger dev teams, which means you're not wasting a ton more human time waiting on CI, and you also probably have developed some tooling at that point that's going to let you do this more easily. So it takes a little bit more work, but for us at least, it was definitely worth it. Now, if you can't do this, or you don't want to have to deal with making your own containers, feel free to skip ahead about 8 minutes. I'll go back to non-Docker topics then. So skip ahead until you no longer see that little whale in the corner. But if you can build your images easily, one thing that's worked really well for us is having a custom Docker image for your CI environment. Now, this will not be the same Docker image that you run in production. It's going to be very, very different. So you're going to need 2 Docker files in your repo, one for production, one for CI. And what you do is you start from a Docker image that your CI provider offers, so it's going to be heavily cached, and you also try to start from one that already has most of the stuff in it, so Ruby, Chrome, whatever you need. And then you add the stuff that you need to run your tests, which is basically the same setup you normally do it in CI. Most of it you do it in the Docker file instead. And the way you will work with this is you will automatically build this image every time you merge to your main branch, and you will always tag it with CI. And in your CI configuration, you point to your registry and to that CI tag so that you're always getting a recent one. Now, importantly, this is not always going to be a reflection of what's in the branch that you're testing right now. These images may take a while to build and you don't want to wait for them. That's key. If you have to wait for them to build before you can run your tests, you're actually causing more harm than good. But since you're always using the same tag, if the last merge to main hasn't finished building, that's fine. You'll be using the one from the previous merge, which is good enough. And also most of your tests are going to run in other branches, but you're using the Docker image from your main branch. So you're also going to have to apply all of the changes from your branch onto that one. So it's important to keep this in mind because there's a couple of things that you will still have to do in CI again after the image starts. So with that in mind, I want to talk about how to do these same 3 things again, but with a Docker twist. First, bundler. As we discussed earlier, your CI provider gives you a cache that you can use to save and restore your bundle install. And this cache is really useful, but sometimes it can actually be quite slow to restore. One thing that can sometimes help is running bundle install on your Docker build. And this means your gems will already be there when the container boots up. And then you don't need the cache anymore. You don't need to do that in CI because you already have the gems in your image. Now there's 2 things to keep in mind. First, this image was built against your main branch. If you're testing in a branch where you've updated the gem file, it won't have those latest gems, so you still need to run bundle in CI. That bundle though, most of the time is going to finish instantly, and very rarely it's just going to install 1 gem or 2, so it's going to be very quick. Now the other thing to note is that you're trying to save time by not needing to do the cache restore, but the Docker layer where you install all of your gems still needs to be downloaded, so you still care about how much space these gems take on disk, or the layer is going to be huge and it's going to take forever to download. Now earlier, when we were using the CI cache, the main improvement for this was deleting old gems. Now that doesn't apply here because you never have old gems. If your gem file changed, your container build starts that layer from scratch, so you don't have any of the old baggage. However, there is still a lot of bloat when you're using bundle install because bundle keeps a bunch of caches that you don't need and they can be quite big, so you want to get rid of them. Now there's a couple of parameters that bundle gives you to prevent those caches, but those have changed over time and I may be doing something wrong here, but it still seems to keep those caches around even if you put in all those parameters. However, a thing you can do is you can explicitly delete those caches after you install your gems, and that will end up saving you the download time. Your bundle install command is going to end up looking a bit like this, and you're going to have to tweak those 2 paths because they will change with your particular system. Now, I'm going to talk a bit more in a minute about how to find those paths and how to figure out how big your layers are and how to make them smaller. But as an example, in our particular Docker build, deleting these files takes this layer from 500 megabytes to 400. We save almost 100 megabytes, which otherwise we would be downloading over and over into those containers. So it's quite a big reduction. It really pays off to do this. And by the way, this is something you can also do if you're not making your own images. If you're doing a normal bundle install in your CI, you can still delete these directories after the install and before you save the cache to make that cache smaller. The only issue is it's not going to be as obvious to find what those paths should be, but if you can find them, that will also help. And so that's how we make bundle faster. The same idea applies to git checkout or git clone. If you remember the problem, cloning the whole repo may take a long time because all the history is coming to it. However, when you're doing a Docker build, you don't care how long it takes. So you can just do a full git clone, and then when the container runs in CI, most of your repo is already there. All you need to do is a git fetch for the branch that you're testing, and that's only going to pick up the few commits that are not already in the image, and that's going to be way faster than even doing a shallow clone. So you might want to try that. And finally, I want to talk about optimizing your layers. As I was mentioning earlier, your container will be composed of many layers, one for each command that you run in your Docker file. And you want to maximize the likelihood that as many as possible of those layers are already cached, and that's why we start from a base image that your CI platform gives you. But there are layers that will almost never be cached, and these are the ones that you added to that base image. And here, there's a balancing act that you want to play. Because Docker is going to download a bunch of those in parallel. Now, how many depends on your CI platform's configuration, and you want to try to optimize for that number. What you're trying to do here is balance the bandwidth that you get for each parallel download stream and the latency of round trips. Let's say you have a gigabyte of layers to download. If you only have one layer that's 1 gigabyte, you won't be parallelizing on that download at all. All of the megabytes that need to come, they need to be downloaded all serially, basically. And you won't be using as much bandwidth as you could. If you have more layers, that download would happen more in parallel and it would download faster overall. However, if you have too many layers, a lot of them are going to be tiny and you're going to be doing lots of round trips between your CI machine and your Docker registry, and you're going to waste a lot of time there. So you don't want to have too many layers. And this is why it's very common to see the double ampersand in Docker files. If each of these little instructions here was a separate run command, each of them would end up as an individual layer. The double ampersand means you're going to run all of those commands and you're going to get a single layer with what's left after doing all of those things. And so that's how you optimize for how many layers you have. The other thing you're optimizing for is the size of those layers in the first place. You don't want them to be huge or they will be slow to download. Now you want to look at the size of your layers, and if they're big, see if there's stuff that you can delete. Some examples of these are temp files left behind from build processes, or those bundle caches, or tar.gc files that you may have downloaded and extracted. You want to remember to delete the tar file if it was big. Now it's very important that you delete those files in the same run command where you create the stuff. Pay attention to those ampersands. Because if those deletions were in a separate run command, then you have one layer where you add all the useless crap that you don't want, and that's going to have to be downloaded later, and then you have a second layer that deletes it. That completely defeats the purpose. Okay, so to do this, you need to see what layers you have in your image, and you need to see how big they are. And the easiest way to inspect this is by using the Docker history command. That'll show you what are all the layers in the image and how much space they take. And if you want to look inside those layers, there's this great tool called Dive that's going to show you the file system of that image and what each layer has in there. And this is really useful to find stuff that was left behind by build processes you can delete, like those bundle caches that I mentioned earlier. And this is also how I found those paths to delete. Here's what that looks like. This is the Dive tool. Up here, it's showing us all of the layers in the image, and we can pick which one to look at. And over there, it's showing us the file system, and in color, the stuff that's new on this layer. And you can ask it to only see new stuff, and you can start collapsing directories, and you can clearly see that 19 megabyte cache directory there. And in a minute, we are going to see, there's the other one. You have another 77 megs. So those are the two paths that you saw me delete in the previous command. That's how you find them. And you delete those two, we save 100 megs. So if your container is taking a while to download, it may be worth inspecting the layers and seeing if there's any low-hanging fruit there that may help. All right, we're done now with tricks to optimize your startup times. And helping your test start faster is one of the most important things you can do that's going to let you parallelize more aggressively and having faster overall times. But I want to talk about a few more things that are important to keep in mind. First of all, observability. As I mentioned a number of times now, CI times are quite variable, and that's because there's a lot of factors involved. For starters, how long a container takes to start depends on whether the particular machine you're running on has the layers cached. But also, sometimes the network is running a bit slow and things take longer. Other times, the machine you're running on is just having a sad day. And because of this, it's really hard sometimes to know whether you're actually making improvements. You may do a little experiment in your CI config, you put in a branch, and it runs super fast, and maybe that's because your experiment was successful, or maybe you just got lucky. It's hard to know because it varies so much. And it's also hard to stay on top of your setup, which over time is going to trend towards taking longer and longer, and you're probably not going to notice that drift unless you're watching it like a hawk, which you aren't. So to combat this, the very least you can do is sample when you're experimenting. Before you try some change, you're going to want to see how long it's taking now. You want to get a baseline. And to do this, don't look at just the last build in main. Look at the last 5, 10 builds over the last couple of days. And notice not just the average time that different steps take, but also the variance. Get familiar with how things normally perform, what steps are consistent and which are all over the place, because those are going to be the ones that lead to sadder builds and the ones that you want to focus on if you can. And when you're running an experiment, re-push to your branch 3-5 times so you can have more samples, and that's going to give you an idea of whether you're actually changing things or just getting lucky. But ideally, you can build some observability over this. It's going to be hard to be specific on what's the best way to do this because it'll depend a lot on your specific observability stack. But as a general pointer, GitHub will send you webhooks when CI steps complete, and you can use those webhooks to build information about timings and push those to your observability layer of choice. And then you can make yourself a beautiful dashboard that's going to let you see with more precision how your changes affect CI runtimes and how they evolve over time. Now, I admit, this is quite a bit of work, but we've had great results with this because it's an early warning system that things are getting slower, and it also gives us much more confidence on the changes that we make. flaky tests are the bane of our existence. The worst case scenario, which a lot of us are used to, is when your tests take forever to run and then a flaky test fails, so you need to rerun everything again and wait forever again. It just adds insult to injury. And no matter how fast you make your CI suite run, if you need to run it again often, you're going to have a sad time. And for this, I have two suggestions. First, RSpec has a feature where it will store in a file the test that failed, and then you can execute it again and run only the failed test. And the way this works is RSpec is going to store the test failures in a file that looks a bit like this. And it's going to use that to know what to run next time. So you can do this in CI. You basically run your test and then rerun only failures in case there were some flakies. And this doesn't fix the problem, but it makes it less likely that it will make your CI red. Now, the other thing you want to do is fix your flakies. And for this, it's important to think about motivations. When you get a flaky, you obviously would like to fix it, like the good developer that you are, but you were actually trying to get something done, and you need to ship that thing, and the flaky is getting in your way, and the thing is testing is actually owned by another team anyway, so you don't really know what to do with it, so you just retry the branch and move on with the actual thing you were trying to achieve. Like, we all do it. We don't like it, but life, right? And then every now and then we do a bug bash or a hackathon or whatever, and we're gonna fix this, but nobody's actually keeping track of what tests were flaky, so you can't fix them either. Like, it's hard to actually get around to fixing flaky tests. But we can do better by having robots that help us keep track of them, and that gives us the right alignment. What you want to do is automatically detect these flakies and create a ticket in your bug tracker. Now, the basic idea of how you do this is once you've run and had failures, you make a copy of the failure file and run again with only failures. And now you have two failure files, one for each run, and they should be identical. And if they aren't, then you have a flaky test. And with a bit of bash hackery, you can find tests that have failed in the first run but succeeded in the second one. Now, don't look at that code too hard. You can find the complete thing explained in the supplementary repo, but you can find those flakies and pass their paths to a utility that will create a ticket in Jira or whatever bug tracker that you use in order for somebody to fix that test. Now, Jira has a CLI that will do this for you, which you can install in your CI Docker file. Other bug trackers also have CLIs, and worst case scenario, you can just curl into their API. And now there's an actual ticket opened by a robot, so it's not even you being annoying or anything. There's a ticket which somebody needs to triage and assign to the right team. And I mean, you'll get prior tests for way later, sure, but now it's visible and it's trackable. And trackable means that it's fixable. We have done this, and it has massively helped us reduce the number of flakies that we have, because now it's a ticket that is someone's problem, and even if you batch them and solve them a lot later, it is way more actionable than having something that gets in your way at the worst possible time that you're just gonna retry and get on with it and move on with your life. Okay, let's talk about uneven distributions. I talked a lot earlier about how setup and startup times are the main barrier to lots of parallelism, because if your tests take a long time to even start, pretty quickly you get to a point where adding more machines isn't really very helpful. But there's also another barrier you can hit, which is tests distributed unevenly between machines. Now, the idea of parallelizing is you're going to go from this to something kind of like that. Now, we got 10 machines, so after setup costs, our tests should take 1/10 of the original time. But this is not exactly what you get. What you get is a bit more like this, because some test files take longer than others, so not all of the machines finish at the same time. And now your CI time is as long as the longest running machine. Now, what you see here is actually pretty good. If you're getting a distribution like this, you got pretty lucky. That little red line down there, that's how much extra time you got over the ideal scenario, so that's not bad. However, sometimes you get into a pathological situation where this happens. Now, this is kind of exaggerated for effect. I mean, you would have to get really unlucky to get this, but you kind of see the idea here. If you have this distribution, adding more machines doesn't really help you that much, unless you get lucky and that rejiggles the files in a more favorable way, but hoping for that kind of rejiggle is not a good situation to be in. And the way to work around this, obviously, is to distribute your files between machines so that the timings end up more even, but unfortunately, this is hard. This is a very annoying problem. I know of only two solutions, and much to my dismay, they both involve mentioning commercial vendors. One of them I mentioned in passing earlier. CircleCI has the CLI tool that helps you split the test between machines. Now, this little tool can split things in many different ways. And one of them is involves storing in a file how long each test took, with a file that is kind of similar to the RSpec one that I showed you for the flakies, and it stores that file centrally, so it will persist it between builds. And then it uses those timings to try and split things more fairly. And it works pretty well, to be honest. So if you're in Circle already, you can do that. The other solution I know of is Knapsack. Knapsack is a commercial solution that acts as an external queue, and each of your machine is going to talk to a queue and pull tests from it. The way it works is they run a server that knows all of the files that have to be run, and each machine is repeatedly asking the server for more files to run. So as a machine churns through files faster, it will get more files. And if you have a machine that's running longer files, it's going to end up getting fewer files, and that evens things out. Now, supposedly, they also store past test timings, and they do a bunch of fancy magic to distribute things better, hence the name, get it? I'm not sure how much that helps. In my uninformed opinion, just having the central queue and the gradual pull is doing most of the heavy lifting there. Now, a side advantage of Knapsack is also that for those CI providers that don't help you do parallelism, you no longer have to keep track of which machine is which and split the files manually. You basically start as many machines as you want, they all pull from the queue, and that makes your life easier if your CI provider isn't. It's not a super cheap solution, but it may be worth trying them and seeing if it helps with your times and if it's worth it. Now this is something I've thought about, but I've never actually tried it, so take it with a pinch of salt. But that RSpec failures file stores how long each test took. After running your tests, you could do some pre-processing on it and make a little file of your own of how long each file takes. And you could persist that file between builds using your CI's caching mechanism that you would normally use for gems. And you could have a little Ruby script in the middle of that command that calls awk that first sorts all of the files by time descending. And if you do that, I think you've made yourself your own poor man's knapsack. Now again, I haven't tried it, so I may be missing something, and from the perspective of throwing money at the problem to save the developer's time, that's probably a bad idea. But if uneven tests are killing you, and for some reason you can't use something like Knapsack, it may be worth trying. Again, it's a wild thought, but under the right circumstances, maybe that helps. Okay, so now we've turned our containers into lean, mean testing machines. They start up super fast, we're running them dozens at a time, they finish evenly, our CI times are amazing, which we can see because we have beautiful dashboards and all of our flakies are gone. And that's awesome, right? We win. But here's the bad news. As I mentioned earlier, execution time can vary a lot depending on how sad the machine that you're running in is, and that will always affect your CI times a little bit. But sometimes you're going to get a machine that is really, really sad, and it'll just take forever to run your tests. Or the network is going to fail you a little bit, and a step that should be instant is going to take 10 minutes. Or literally forever, it may get stuck and it never actually finishes, you need to actually go and cancel it manually. Now this doesn't happen often, but when it happens, it's really sad, and it kind of negates a lot of the improvements that we've made. And so here's the bad news and the sad part. The more machines you run in parallel, the faster your test will finish. But also, the more likely it is that one of them is a sad one, and that one's going to take a really long time. Now again, this happens very infrequently. But if you're running, 64 machines, it'll happen on many more pushes than if you're running in 4. So you need to keep an eye on that, because the more machines you add, the faster your things will run until you hit a point where things actually start taking longer on average because of this problem. And sadly, there isn't a silver bullet for this. This is a classic trade-off. The best we can do is to have good observability, which is going to let us figure out what the sweet spot is that is going to give us the lowest CI times on average. And finally, I want to make a quick note about critical paths. Depending on the complexity of your project and how much tooling and automation you've developed, you may have a CI workflow that is quite complicated. This is ours. And one thing that is kind of obvious if you think about it, but it's very easy to lose sight of, is that the only thing that you care about is how long it takes to get your branch to green. You don't care how long it takes each individual step to be green, you only care about how long it takes for the last one to be green. So you should focus all of your efforts on the steps that are in the critical path for that. Now in this particular workflow, these 3 are the only steps that matter. optimizing anything else is pretty much a waste of effort. Now, for example, it's possible that we could make this secrets step go faster. I mean, it's taking quite a while, but that's not going to make the overall workflow faster, so you shouldn't bother. And this is especially true if you're making steps faster by adding parallelism, because now that makes it more likely that one of them will hit a slow machine, as I just mentioned, and now you've shot yourself in the foot. Because for the steps in the critical path, there's a sweet spot of parallelism where you balance the time that you gain with the risk of a sad machine. But for the steps that are not in the critical path, if they are using any more machines than they absolutely need to, you're getting all of the extra risk with no benefit to offset it, because you're not going to get to green faster. And you're also spending more money on those machines, which, again, you don't get any actual benefit for that. So focus on the critical path, ignore everything else. Now, of course, as you make a step faster, you may remove it from the critical path, and that's amazing. Make it no faster than that. Focus on the new critical ones. And importantly, this means not only making steps faster, but also considering the dependencies between them. There may be ways of restructuring your tasks so that one of your steps no longer depends on another, and you can gain a huge amount of time for this. And this is very typical if you have, for example, a setup, bundle, and yarn job, and then you have a bunch of other steps that depend on it. If your unit test step is the slowest one, and it is depending on setup, bundle, and yarn, that may be a bad idea, because it probably doesn't need yarn. And so you can make only the steps that do need it depend on it, and save yourself some serious time on the critical path, which is the final time to green. And the same goes for jobs that use a lot of different containers for the dependencies. It's common for only a few tests to need all of those dependencies. You can separate those tests out into their own job, and you only add those extra containers on that job, like we did with search at the beginning of the talk. So the rest of the tests don't really need to wait, in this case, for Elasticsearch to boot up. So that's pretty much what I wanted to cover. To do a quick recap, you want to parallelize a lot, but focus on optimizing your startup times. And you can save time on bundle install, git checkout, and your container spin-up time. Build your own images so you can have absolute control on how all those things work, but keep those layers tight. Optimize your dependencies, improving your critical path. Keep an eye on your runtimes over time, and get rid of flakies by putting them in your backlog. And that's it from me. I've covered a lot of different techniques just now. Some of those will hopefully help. Again, your mileage will vary. Some of these will help in your particular scenario, some won't. But hopefully this will give you some ideas on how to approach the problem, and some combinations of these techniques are going to allow you to reach CI bliss. Thank you.